So anyways, yeah, so it agrees with what we know already in this sense. So that's good. I guess that's all you need in terms of validation. The other thing I want you to mention in connection to this is it's a leap that we are going to make. So when you look at this expression, it should raise a kind of a question. When you look at this, kinetic energy is 1/2 mv squared. You'll be okay just leaving it as it is. All right, good. That's the kinetic energy. We are done. When you look at this expression, it's oddly and maybe even unnecessarily complicated. We are not saying, so actually maybe this will be a little bit clearer if I write it out this way. So I factored out mc squared, gamma minus 1 times mc squared. So maybe you're looking at this as one thing. Let me expand it out. Expand it out, it says this. Relativistic kinetic energy is equal to gamma mc squared minus 1 times mc squared. So that would be just mc squared. So this is the expression for relativistic kinetic energy. It's oddly complicated. We are looking for one thing that's expressed in two terms. It's like, sorry, I'm not good at analogies, so I shouldn't try. But, we are looking for one thing. And when you look at this, it's a nice one, tidied up ribbon that, you wouldn't look for any missing pieces. This is an expression that invites looking for the missing piece because it's something that you think is one thing, but it's expressed in two parts. So I'm making a leap here. I'm making a leap to say, maybe the relativistic kinetic energy really isn't really a one thing. Maybe it is actually a difference of two things, where maybe, so before we are used to saying kinetic energy is the entire energy in the absence of potential energy, Like when this is here, right now, in this state, it has zero energy. And once it starts moving, it has non-zero energy. We are used to saying that. But what I'm saying, this form is inviting you to say is that maybe relativistic kinetic energy, that's not the whole thing. Maybe what we want to call the whole thing, whole energy, is this. This is our total energy. And what relativistic kinetic energy is, it's not the whole energy. What kinetic energy really is total energy minus this. Or you could say this, that total energy is equal to kinetic energy. It's one portion of the total energy plus this something else. And in terms of mathematical expressions, it would be this. So the total energy is gamma mc squared is equal to kinetic energy. Let me just write it down as kinetic energy. Kinetic energy plus this is something else, which apparently is mc squared. Yeah. So, I'm not saying this proves it, but the way kinetic energy can be written in this form invites this kind of thinking, right? That there's some form of energy that we have never previously identified. It's not part of the kinetic energy, because to get to kinetic energy, you have to subtract this out from the total energy. And it's not part of any other form, because so far we haven't introduced any conservative forces, any potential. So this is not really a potential energy, as you would call it. So there's a term to describe what kind of energy this is. This is what, if you took physics 4A with me, what I called rest energy. It's an energy that, well, let's see what it depends on. See, that's a constant of nature. Depends on mass. So it's an energy some object has just because it has mass, just because it exists. So when you work out the numbers, it'll turn out to be quite a bit. Like this tennis ball weighing, I don't know, having mass of 100 grams or so, has more energy than what's released in, I don't know, hydrogen bomb or something. So it's quite a large value. And at least prompted by the expression, we're saying, well, this has some form of energy that's quite large. And you might call this as just the fanciful thinking, except for the fact that you see effect of this in nuclear reactions. So when unstable isotope breaks into smaller pieces, you count up all the masses, you see that mass of the daughter nuclei are less than the mass of the mother nucleus. And they gain the kinetic energy. The kinetic energy came from the rest energy of the initial heavier nucleus. So because for a very small amount of mass, it's such a large amount of energy, you don't see the effect of this in most interactions. You don't see it in physical interactions. You don't really see it in chemical reactions. But in nuclear reactions, there's large enough change of energy that you see the mass changing effect of this rest energy being released. But this is our new picture. That's kind of a, I don't know, fanciful guess, at least initially. But as we talk about quantum mechanics and give you some numerical examples of nuclear decays, you will see that this is not just a fanciful idea, that is a form of energy. And I guess what it is it's kind of a manifestation of potential energy that represents potential energy involved in nuclear interaction. So you might have seen this popular expression. It's that, it comes up with when people talk about Einstein. You might have seen this popular expression, E equals mc squared. And if you know me, you know that I have a very low opinion of what counts for popular science. Essentially, I trust nothing that's published in popular science magazines and newspapers. It comes down to people writing those don't understand physics. Like, imagine how much education it took to get you to here. People writing those articles have half your level of your science and math education. So they couldn't have possibly understood what they were writing. So I don't trust anything that they write, science-wise. Maybe other things too. But so this taken at face value is wrong. To make it correct, you can do one of two things. You could make it correct by putting in this gamma here, because yes, that is total energy. Gamma mc squared is the energy, including the kinetic energy. You could make that correction, or you could say that rest energy is mc squared. So with those two corrections, that's correct. But I guess usually, within the limited application of that, when you see change of mass that represents change of energy, then sure. But you just have to be careful that the E here is not supposed to be the total energy. It's the rest energy. Yeah. So you are actually going to see this more when we do quantum mechanics, and as we do more examples of collisions and whatnot, you will actually see this more. It turns out mathematically, I guess we might not get to this part. If we get to this part, you will see that the mathematical behavior of total energy, it's much more nicely behaved than the kinetic energy. So you are almost never going to see me trying to work out kinetic energy directly. If some question asks for kinetic energy, it'll almost always be a two-step process. I will first work out the total energy, and then I will figure out the kinetic energy from here, total energy minus the rest energy. That's how I would usually figure that out. So yeah, so that's a relativistic kinetic energy. That's I guess the first correction to the non-relativistic mechanics that you've known. And you can imagine making this correction for everything else you know, to gravity. I guess, is that it? That might be it. It's indication of how little fundamental physics we've taught you. But because the only other fundamental physics we've taught you is electrodynamics, and I just told you that that doesn't need to be corrected. And anything like dealing with the things like spring forces, these are not fundamental physics. So, but now that you know about relativity, what you have to approach with is any other piece of physics that you used to know, you have to, the first time you see it again, you have to ask the question, well, what is the relativistically correct version of that? So when you see momentum, you have to ask, what is the relativistically correct version? That's this. When you see kinetic energy, you have to ask, what's the relativistically correct version? And that's this. And I don't know what else, yeah?